We have our last guest for today for the Mercury stage. I'm pretty sure maybe the other stages are also finished or are finishing right now. And once again, we are blessed for the second time in this event with Clifford Agius. Hi. He's perfectly, thank you. Also a little bit tired. He also had a session yesterday. And well, the first thing that I always want to say about you, Clifford, is that you are, well, a pilot. For all I know, a senior first officer, right?
Yes.
Yeah, and you do a lot of other stuff. You are a .NET developer and so on. So your description is foot long.
I try and shorten it, but I do too much stuff.
Anyway, so yesterday you talked about one thing, and today we're going to hear about 3D printers, or most likely 3D printed Bionic Hand.
One of these.
Yep. Okay, so you have an example. Okay, so the stage is yours. I'm leaving you for the show, and let's see what you got.
Okay, thank you. Hi, everyone. My name is Clifford Agius, and I'm here to talk to you about a 3D printed prosthetic hand and how I went through building and designing the whole project. I normally take a little bit longer in giving this talk. I've only got 40 minutes today, so I'm going to be fairly quick and go through the slides quite sharpish. And so please try and keep up, and some good Q&A at the end, hopefully. So. If I click on mid slides, it's already been mentioned that I'm an airline pilot. I get to fly the 787 aircraft around the world for a major UK airline. So that is my office. I'm not mentioning it. It was mentioned anyway, so it's taken out of my hands, but I'm not mentioning it because I want to show off. Look at me, I'm an airline pilot. There is a reason that I mention it in this slide deck, that I'm an airline pilot, and I'll come back to that later on towards the end. When I'm not flying planes around the world, so I work as a .NET, freelance .NET developer, mainly in the IOT and mobile space, so Maui and Xamarin, but I get involved in all sorts of back-end stuff mainly. I'm not very good at front-end things. Having said that, .NET and Blazor is coming onto my radar more and more. And we're not doing that. I love playing with electronics. You can see my bench behind me, where I get to solder things and build projects for clients and customers. And I spend time with my family, and we'll talk about that as well as we go through this talk. But that's enough about me. Let's meet Kayden. Now, Kayden is a happy-go-lucky teenager. We started this project some years ago, and as you can see there, he's a member of the Scouts here in the UK. And as I'm sure you know, the Scouts are around the world. So you can see he's always getting involved. And you probably noticed in the picture there where he's going into the lake for the umpteenth time, I'm told, that he's missing his left arm. So his left forearm from just below his elbow is completely missing, and it's something he was born with. So he doesn't have that part of his arm. And if you look in the picture in the centre, you'll notice that on his other hands, he's missing all his middle fingers. So he's got his thumb and he's got his pinky, but the other ones are as if he's got his fingers crossed. They don't exist. You'll also notice in that picture as well that he's got a metal hook that he's holding his wrist in, and we'll come on to that as well. This is Kayden going to the 2012 Paralympic Games, and that's his party trick. So he would clip his arm, his prosthetic that he's given by National Health Service and NHS here in the UK. He would clip it onto a bar and step away from it, and everyone would go, "Oh, that kid's arm's has just fallen off." But no, that's just his party trick. But it shows really well in that image of what he's given by the National Health Service. He's given an arm. You can see in the lower picture there's a red one and a green one, and that is because every year he goes back to the hospital and they take a cast of his arm, the part he has left from the elbow onwards, and then they create the rest of the arm from that. Then the hook on the end, you'll notice the hook that's on the bar of the underground there, that is just carried forward to the next arm. But that section that they make costs between £4,500 and £6,500. So what, 7,000 to 8,000 euros around there somewhere. And then the hook on the end is 1,500 to 2,500. So again, around 2,000 to 3,000 euro. So they're not cheap. a National Health Service have to cater for, you know, as any health service anywhere in the world, has to cater for a lot of people, and they have to make a decision on whether to give a child an arm or to give someone some life-saving cancer treatment. So, you know, these items are not very cheap at all. I've kindly been loaned the arm, that the red ones you can see there, because Kayden doesn't use it. He's grown out of it, so his family have kindly loaned it to me. But as you can see here, you've got the string. You can see it in the image there as well. And this strap goes across his arm onto his other shoulder. And as he moves his shoulder backwards and forwards, it pulls the fishing line. And there is literally a 100-pound fishing line. And it pulls the fishing line and opens and closes the grip, as you can see there in the image. So that is all he gets. That's what he gets. This section, this middle section, gets replaced. And that bit he gets to keep. I've managed to persuade the hospital to give me an old one. You can see this one is bent and damaged. It's actually about to snap. So they kindly let me keep this one because I'm doing these presentations and talks when he got a new one. So that's what he gets from the National Health Service. So where did this start? Well, back in Christmas 2016. So the project's been going for quite a while now. This news article appeared on the news media here in the UK. It was about a dad that 3D printed a prosthetic arm. So just after the school holidays, I was back at school with my two kids, and my boys went to the same school as Kayden at the time, and his mum, Sharon, grabbed me in the playground and we were chatting about things and how Christmas went. And she said, "Oh, did you see the news over Christmas about the dad that 3D printed a prosthetic arm?" So I didn't see that at all. "You've got a 3D printer, haven't you, Cliff?" I was like, yes, I have. Yes, I have, Sharon. Knowing instantly that what she was asking was, could I help print an arm for Kayden? Sharon was, you know, the head of the PTA. She was the person you went to if you want anything done in the school or locally. She knew everyone, and she wasn't the person you said no to. So I fired up the 3D printer and see what we could do. So let's find out how Kayden uses his arm currently, or did at the time. So we've got some video here. Hopefully you don't need to get any video. Here, I went round and shot it on my phone. There's Kayden making me a cup of tea. You can see he's quite dexterous. You know, he's got a cup out, and he's down a tea bag from the pot tea bags. You can see he's always using that that shoulder to move in and out. So actually, that's the same arm as the one I've got here now. He's become quite dexterous. The reason he's become dexterous with it is because he's been using it for many years. From birth, his parents were very instrumental in getting Kayden onto a program within the NHS, National Health Service, to make sure that Kayden got the best that he could get, the best technology, etc., etc. Now, the NHS are not going to provide a full prosthetic arm, biomechanical arm to a child because they grow. And they grow out of it. Every year, Kayden has to go back and get a new arm. But because he got onto this program, they helped him. So from birth, he's always had a prosthetic. Literally, you see the baby ones, they're kind of really small. They're quite cute. But when you think about, you know, the reason they've been made, they didn't actuate. They were just solid lumps of plastic. But it gave him something he could crawl about on and get used to. So again, we took the idea from Sharon. We did a bit of Googling and looking around. And if I bring up my my browser, wherever it's gone, is which one is it? This one here. We did some Google and Bingling around, as you do. And the first place we come to, linked from the news media sites, was this Limbless Association. Now, when we first started searching, this page had a massive banner that said under construction. And until about 9 months ago, it was under construction. So for 3 or 4 years, this site was under construction. But thankfully, the developers finally got to release the build, and you can see the website here, which is great. It tells you about the different charities that exist, but doesn't tell you about something you can go and print. So a little bit more searching around, and we eventually found the website. No idea why the news media didn't link to this to start with. I don't know. But we eventually found the team Unlimited. It's a play on words, unlimb, because it's a limb. So we found this website. They're on to Isabella edition. The edition they had a few years back was a slightly different version. It's a lot more difficult to print and build. It had more components, etc. But this arm you can print and make, and we made a version of it, which you can see here. I'm holding up to the screen, and what that works is the fact that it works on the same principle. Is the fact that you can see that the strings pull, and then as you pull the fishing line again, it opens and closes the grips of the fingers. Now, Kayden didn't like that because we printed it and tried it out. We even glued on the spigots so it clipped into his arm at the bottom here. But as you can see in the image, when I close the fingers, they don't quite grip. And there wasn't much he could do. He could carry a carrier bag, for example, or his school bag, but it wasn't much he could do. So he hated it. Within minutes of trying it, he took it off, said, don't want it, keep it, go away. It's like, brilliant, okay, great feedback, Kayden. We'll go and we'll try something new. So then we searched some more, and we come across the Open Hand project. The Open Hand project is Joel Gibbard did this as university projects, and he basically put motors into the back of a 3D printed prosthetic hand. So it's very crude in the pictures, wasn't very good. We tried printing one, and again, the printer struggled. We managed to get one printed, but then trying to get components and parts are a bit, difficult to track down. So we always carried on looking, when stuck in a hotel somewhere around the world, always be looking and searching. Eventually found Joel Gibbard was linked to a company called OpenBionics. And this was moved on from the Open Hand project to starting a company called OpenBionics. And as you can see here, this is actually a librarian. She's got two of their hero arms, which they now sell around the world as a product that you can buy. They don't give a list price on there because it depends on how they customize the grip that fits different arms, but anywhere between 10 and 15,000 a piece. So still similar price to what the NHS provide for the hook, give or take a bit, but still not very cheap. And by now I'm starting to think, well, 3D printed parts are super cheap. We're not talking a lot of money at all. I want to make this so cheap that actually I can take it somewhere around the world when I go flying. This is back to where I'm starting to think about being an airline pilot and what I can do. Thankfully at the time, OpenBionics, it's open, it's in the name. They had a GitHub. You can see here that the GitHub was, if I zoom in a bit, you can see here the last commits were 3 years ago and 4 years ago. So quite a long time ago was the last time they were committed any changes to their repos. And they went from being open source to closed source. And I used to complain about this in my talks, but I'm understanding now from talking to various different people that they had to do that because they had to control it so they could get the products certified around the world. So good luck to them. They're a business and they're helping and changing a lot of lives, including that librarian. So hopefully they can change more lives. But I want to do something slightly different. But the good thing is they left it all on GitHub. So we took these designs, we printed them, and we fired up the printer, and this is the first component that come off the printer. You can see it's not very good. It's pretty poor quality, and that was on my old RepRap Mendel. It just wasn't up to the job. So what do you do when your tooling's not good enough? Obviously, you upgrade. So I upgraded and purchased a Prusa Mark III printer. I bought the kit version so I could build it myself, so you can learn a bit more about how they're built, plus my RepRap Mendel was home built as well. You can see I've circled the blue part there. That was because when I was building this, I snapped that part from the kit. But Prusa just sends you, if you have a 3D printer, it just sends you the STL file. So my RepRap Mendel is carried forward because it printed that blue part, and it's still on my printer, it's just up to my left here. So there's a bit of history going through the printer there as well. So we printed all the components. You can see there the white parts are the PLA plastic, polylactic acid, so it's a vegetable oil derivative, and they're all 3D printed parts. Quality is much better with the Prusa printers. I've not seen any printers print as high quality as these, other than full industrial machines. You can see in the top left corner there the 4 Actuonics motors, and they're just little linear motors that just move in and out by 20 millimeters. and they've got an inbuilt potentiometer, which gives you variable resistance, so you can see where in the range they are. And then we've got various screws, springs, etc. And then big bag of brass inserts. If you do any 3D printing and you need to screw something in and unscrew it and screw it in again, you typically use a self-tapping screw. The problem is that the plastic becomes worn out after a while. 2 or 3 goes and that's about your lot. With those, they're machined brass inserts from a company called Inserts Direct, and you literally push them, melt them into the plastic with a soldering iron, and then pop the soldering iron out, and they cool down and become part of the plastic. And then you've got a machine thread. You can screw the screws in and out as many times as you want, and they're fantastic. Super cheap. You have to buy them in a bag of 1,000, but even then they're super cheap. So we use those. So this is a 3D printer. We obviously need to connect it to Kayden because now we have a hand, so we need to connect the sockets. You can see there's 5 hours and 45 minutes remaining, as you can see in the image, 545R, and it's about halfway through the print. You can see the SD card image is 50% on the image there. So he's like, brilliant, let's go to bed, and in the morning it'll be finished, because I'm not going to sit here for 6 hours and wait for it. In the morning it had popped off the print bed, and it left the spaghetti mess that anyone that's used a 3D printer is well aware of. Happens from time to time, and all that happened, it popped off the print bed. But as you can see in the middle image, it had printed just enough for us to test. So we took it around, tried it on Kayden, and it was too small. So you can see in the right hand image, we made it bigger. Then we just went into the slicing program, into the Prusa slicer, and just made it bigger, scaled the scale up a bit, printed another one. 6 hours later, we had a new one. We tried that on Kayden, it was too big. So in typical nursery rhyme style, we printed a third one, and this one was just right. So version 3 was the design that worked for us, and Kayden said it fitted better than the prosthetic that the NHS provided. So that meant that we had a way of connecting to Kayden. We had a hand, we had a socket, and then we just needed the center part, which we designed and printed, which is one of these here. So this is the arm, and then all we do is for anyone else is we just make this arm longer or shorter, depending on how much of their real arm they have left. So we can make that longer or shorter. In Kayden's one, we've managed to hide the battery inside the arm, so the battery just slots in, and we connect those two together. So that is how we've made the 3D printed parts. Let's talk about the prices though. If you look here, we have the price. The top section, lines 3 to 10 on this spreadsheet. You can see there all the molds, and the molds are, if you look at the hands, you can see all the white plastic printed on it. You see all this black stuff that we've molded on. This here is it's like neoprene rubber. It's called Fileflex 98, I think it is. And it's basically, it's the same stuff that Hollywood used to make like a Klingon mask, for example. So it's the same soft, squishy rubber. And the idea is, because this is albeit Lego plastic, and we know how smooth and that is, it means you can't grip. So we mold this black plastic onto it. So we have a mold which is like this. This one here I printed. I've only ever made one of these. This is for the palm mold, so the base plate one. And so we make all these parts. We fill the reservoir with the plastic. The 3D printed part goes inside, and we screw it down. And then we just push the plunger down and it molds it on. We leave it for 24 hours, pop the cover off, take the part off, a little bit of a skill blades to clean it up. We'll have a new thing. I've made all the molds. They cost £10. You can see there, so what, 11, 12 euros. And I'm still on the same set of molds. Yeah, I've made about 15 or 16 of these hands now. So that is a price that's carried forward. It's a one-off cost unless you break them. The middle part though, lines 11 to 20, is the actual cost of printing the white plastic parts of this hand, and that costs £5. What's that, €6? And that's it. So £5 compared to the many thousands for the arm. So this is kind of, it's game-changing time. The red elements of the hand, as you can see in here, these are the flexible plastic, so they're printing a different material, so it's flexible. And I'm still onto the same original spool of plastic, because you buy it in a 1 kilo spool, and you're using what it's about 7 grams of plastic. So I'm still on the original smaller plastic there, and that costs 20 pence. So for £5-ish, €650, we've got all the 3D printed parts that we need to make a prosthetic arm. But now we need to control it. So how do we do that? OpenBionics had this called the Chestnut board, which was an Arduino compatible SAMD microprocessor board, which they designed in-house, and they were having produced for them, but they cost £250. They had a store at the time. They no longer have a store because they've gone closed. So they don't sell these boards anymore, but they never had them in stock. I waited 3 or 4 months and then they were never in stock. So I thought, it's not ideal. What can we do about that? But how did they sense the muscle movement? Well, you use these boards called malware muscle sense boards, and what they do is they connect to your arm or to a muscle, any muscle on your body really, but obviously we're detecting the arm movement, and you place it on the muscle, and as long as it's in the center of the muscle and the little fly leads, it can go back. You can see the little fly lead, the little lead that comes off there, connects to the myotendon junction, which is basically the end of a muscle, so the bone, like the elbow for example. Then you get a good sensing signal. You can see there, the green one in the middle is the correct placement. But if your midline offsets are slightly to the left or right of the center mass of the muscle, or you've just moved up or down the muscle, you're not perfectly in place, the signal you get from the board is it's quite poor and not really usable. Added to that, those boards you need 2 of the muscle boards, one for open, one for closed. Each of them has 3 connectors. If I go back to the previous image, you can see there's 3 little sticky pads. They're just the same sticky pads you have if you have an ECG with your doctor. So every day we need 6 sticky pads. A bag of sticky pads costs £5 for 50. So not expensive, but that pack of 50 is only going to last you just over a week. So it's a cost ongoing, and I wasn't happy with that. Plus those boards are £35 each, so what, 37, 38 euro. And you need 2 of them, and you're sticking them to a child's arm. They're not going to last very long, are they? Let's be honest, they're going to break. So this is not scale, it's not man muscles, they're nowhere near as big as that. But yeah, you can see where you need to stick them on the arm as well. So we stick one on the inside of the forearm, one on the outside of the forearm, and this is the audience participation time. What we need to do is stick your arm straight up in the sky like this, with your hand pointed up and your palm facing towards you. Yeah. We take your fingers, little pincers, and I want you to stick them either side of your elbow. Yeah. And then I want you to open your palm away from your face, and you'll feel the muscle there go tight to the back. Close your arm, your palm face towards the floor and away from you like this. You'll feel the muscle at the front go tight, the one inside your forearm. Yeah, you hold your hand straight up and create a fist. You'll feel that both muscles go tight. So what we do is we sense that is open because the palm is open. That is closed because the palm is closed. And the grip is to change the next grip in the grip sequence. So now we have a way of controlling our hand and our grips. So we have open, we have closed, we have different grips. OpenBionics come up with these 5 grips. They did a lot of testing and checking and worked out these are the 5 grips that most people use. You can see there. But imagine only having 5 grips. You've got 5 grips, and that's all your hand can do. Pretty limiting, but still better than the hook that Kayden had. So let's look at how that's created. This is the software that's inside the boards. It's slightly modified in our version, but this is what was in OpenBionics Beetroot software, as they called it. You can see here, now us as software developers could work this out. It's a 3D array. So there's a counter on the left-hand side. You see the count from 0 to 100, and that counts over a time that you specify in memory. So for Kayden, it's 1.6 seconds, I think it is. It actuates the movement. So as it counts up from 0 to 100 over that course of 1.6 seconds for Kayden. F0 is the thumb, F1 is the first finger, second finger, third finger, fourth finger. Fingers 3 and 4 in this hand, it's a child hand, are linked. So obviously the software is designed for an adult hand because you have more width. So as it moves between fully open and fully closed, you can see these grips. You've got palm grip, which is where you can hold the carrier bag. So everything's open, but the other fingers go closed, so you can hold a carrier bag or your school bag. Now, if you wanted to create a grip for say an Xbox controller, which is what Kayden wanted. He asked for fairly early on in the project, for obvious reasons. You as a software developer, I've basically explained this to you, and you can, well, brilliant, I can do that, Cliff. Off you go with your laptop, and you could create a new grip. You play with it a bit, you'd upload it to the hand, you screw it all back together, and you'd be quite happy that you can create a new grip and code it down to the board. You've got Visual Studio or VS Code loaded onto your laptop. You've got all the appropriate USB connection software. You know how to run the Arduino code. You've got the skill set to be able to create a new grip. But does a parent, does a doctor in a hospital, some part of the world, do they have those skills? Probably not. So again, these are just little things that I'm chalking up to I want to change and fix. So I went away and thought to myself, I need to come up with a better idea, a better bit of electronics. And I use a lot of Adafruit tools. If you've not heard of Adafruit, they come out of New York, out of Manhattan, where they're manufactured. This board here, the Feather Bluefruit, is one of their boards that they make. In the Feather system, all the boards are the same, except you see the red section, the bottom corner there, that is the Bluetooth sender. So now we have a Bluetooth and we have an Arduino. It's got the same SAMD21 chip on it, so exactly the same chip that's on the OpenBionics board. So there was very little in the way of software changes that need to be made to make the software run on this board. And then we added some code to make the Bluetooth work. Some specs on this, it's very small. They call it a feather board because it's supposedly as light as a large feather. I don't know which kind of bird they're taking that feather from, but there you go. And the only part on that list that you may notice is the no EEPROM on the fourth line. There's no storage, which come back to bite me later when I wanted to store new grips, but we found a way of doing that in memory anyway, using a flash storage mechanism. And we overcome that, but otherwise it had everything we needed to be able to do it, and it's a much smaller board as well. So there you can see we soldiered it together. The second board, the one above it with the two very large sealed capacitors, that is the Adafruit Feather motor controller board, so that allows you to control 4 motors, which is lucky because we've got 4 motors inside handy. You can see there that we've connected all together. We had a bit of trouble in the image to the right. You can see the fact that the ribbon cable that comes from the motors doesn't really like to be soldered through hole. So we had a bit of trouble trying to get connectors for that, but eventually we found those, and we connect. You can see them at the bottom in the red circle, and we soldered them as well. The Polyloo board, the top circle there, what we do is we take voltage from a 5-volt battery. So we take a 5-volt 10,000 milliamp hour anchor battery back. We've all got these. You've probably got one in your backpack with you now. We take 5 volts from this. We step it up to 12 volts, which powers the motors, and we step the 5 volts down to 3.3 volts, which powers the electronics. And why do we do that? Well, OpenBionics use a 14.7 volts battery, which you often find in RC cars. So, yeah, okay. I'm suffering from COVID, by the way, which is why I'm not with you there in Vilnius. So I've had to stay here. So we use these Polyloo boards. They're very inexpensive, very cheap, and we can use a step the voltage up, step the voltage down. We use a bog standard 5-volt battery pack. The only downside is that this can charge your phone. So Kayden often sort of gives up time that his arm's available to charge his phone or his friend's phone as well. So yeah, that's one problem. But hey, what can you do? They're teenagers. So we listed the drawbacks. The single source boards, the processor. We've managed to cross that off. We've now found a board that works. But what about these malware sensors? You know, to sense a muscle signal. I remember the flight. I was flying to Japan, and I read the Hackspace magazine. If you don't get it, and you like anything to do with IoT and tinkering and playing, Hackspace magazine is awesome. Highly recommend it. I was reading this, and you'll notice that Graham Morrison was given a written article, and he using these piezoelectric sensors, which are used in electrical drums or used in demolition. Explosive demolitions to see when the explosive went off, etc. But he was using it just as an input into an Arduino board, an Arduino Uno, and I took these, I landed in Japan, I ordered a pack of 10 for £1 from Amazon, and they beat me to my house by the time I got home from Japan a few days later. We connected it up, and Kayden didn't like it because you could no longer control where the hand stops in the grip sequence. So a bit more looking around, and via Sparkfire Electronics, we found these full sensitive resistors. £6 for a pack of 2. You can see in the GIF, whatever side of the fence you sit on there. You can see there, as the pressure's applied, it changes the resistance, and using the resistor bridge, you can then sense that in analog inputs and change sensors. So again, we bought a pack of these. Again, I got them from Amazon because they're delivered next day by the magic postman. We tried that, and that is now what is fitted into the arm that Kayden has. Now fitted just inside the socket, so just inside either side here. I'm not sure if you can make them out in the picture, but just inside. So as his arm goes tense and his muscle goes tense, it squashes against that sensor and change the resistance, and therefore we can read that into the board. This is the circuit, a Fritzing diagram of the circuit. It looks complicated, but really it's not. You've got the motor controller board on the right, and that controls the 4 motors. The blue wires are the analog inputs into the main boards, which is the one to the left, and we've got the 2 Polyloo green boards at the top. One stepping up to 12 volts to supply the motors, and the other one, the slightly larger one in the image, is supplying the 3.3 volts to supply the supply voltage to the 2 boards. And then the grey circles at the bottom are the 2 force sensitive resistors, which just below where it says wire 31. I did try and clean this up, but no matter what I did, it always looks a bit of a mess. You can see that it's a fairly simple circuit. I can build that circuit now in about an hour. I think anyone that doesn't have soldering skills will probably take 2 or 3 hours, but it's buildable by anyone, and it's on my GitHub if you want to go and make one yourself later on. So now we've covered off the malware sensors. We've got rid of the sensor pads as well, so you don't need the sticky pads. You remember I mentioned about the ECG sticky pads. We've got rid of them as well because those sensors don't need any sticky pads. They're glued inside the arms. As soon as he slots it on, it's good to go. There's no sticking expensive boards to a child, so we've got that covered up as well. But how about that last thing we said about programming a new grip? Kayden wants his Xbox grip, doesn't he? How are we going to do that? How are we going to program it for a young girl, another person that we've managed to help with one of these arms? How are we going to help them with a grip that they want for something they do? I mentioned at the very beginning that we had Bluetooth on that Adafruit board. Bluetooth, if you've never played with Bluetooth, I've just grabbed some images from the internet for this slide. There's so many different acronyms around Bluetooth. It's crazy. You get Bluetooth Low Energy and Smart and everything else. Ultimately, though, the way Bluetooth works is you have your central device, in this case a mobile phone, and it connects to a peripheral device. So be that your watch, if you've got a smartwatch, be it your car, be it handy, as we call it. So this is what we wanted to do. The way it works is for Bluetooth Low Energy, it's still called master slave, even though we as an industry moved away from that. The master client is the central client, which is the mobile phone. They agree a connection interval between the master and the slave. The master will send a request to the slave will respond, and then the slave will go to sleep until it knows that it needs to wake up again X milliseconds later to listen to the master for another request again. Which it will reply to, and that's why it's low energy, because it spends a lot of time asleep. You can see there the connection interval time, it sits asleep quite a bit at that time, so it saves a lot of energy as well. Inside, it's a bit like a class, so you got your profile, like your namespace, services like your class, and your characteristics like your properties within that class. So you can look at the characteristics and take a smartwatch, for example, have a characteristic of how many steps, you can have a characteristic of the heart rate, you can have a characteristic of how many times you've been up and down the stairs. All those sorts of characteristics will be in there, and you can just read and write them depending on the settings that are around, whether it's read only, etc., etc. So normally I go into Visual Studio, but I'm aware of time and we don't really have time for that. So I'm going to skip past going into Visual and looking at code, because I'm pretty certain you want to see handy move. So now we've got the Bluetooth from the mobile phone connecting to the Adafruit board. We need a mobile app to control it. I mentioned before that I spend a lot of time playing with Xamarin and now Maui when it comes out in next year. as part of the .NET 6.7 timeframe. So I obviously went with Xamarin. It works on all platforms, which is good because his parents had iPhones and Kayden had an Android. I'm an Android user, so it meant I could write the code once and it would work across all their devices. And also it would work on desktop as well. So a PC using UWP, which meant that in a hospital environment, they could use the hospital PC for programming the hand as well. It's .NET and C#. I know that. I love that. Brilliant. Great, we're going to use that. And added the last line there is accessibility. We want to make sure that it's accessible to all. So Kayden has his text slightly bigger because he's only got his thumb and his index finger that he can punch the screen with. So he has the text and the button slightly bigger, which meant that Xamarin took care of that for us as well. So obviously pick Xamarin. If you've not worked with Xamarin before, highly recommend it. Certainly when we go across to Maui in the new year. You've got traditional Xamarin, which is where you have a C# backend, think of that your service and your data layer. And then the UI will be written in the different frameworks for Xamarin, iOS, and sorry, for Android, iOS, and Windows. Or you can write the Xamarin Forms, which is shared UI layer, where you do it in a Xamarin or Maui style XAML. And then it's shared across all the different platforms, and it looks the same on all the different platforms, which is what I went with Xamarin Forms as well. So again, I'll pop out of Visual Studio and show you that, but we're tight on time, so we'll go from that. The way it worked though was I would write the codes and I would push to GitHub, and then App Center, which is a free service from Microsoft, would look at the GitHub branch and would pick up the fact that there's a build, and then we'll pull that build in and build it and then push it out to the test developers, which would be Kayden, his parents, etc. And from that, we would be able to get the code out to their devices. So we would you know, merge the code and push it out to them. App Center is phenomenally good. It's not as good as what it is in this slide anymore because things like orphan data have been pulled. They've been pulled back into Azure as opposed to in App Center. We'll go on that. So now we've managed to cross off all the drawbacks, the processes to others as well. And Kayden has now got his Xbox grip. This was us playing on the bench a while back and making the Xbox grip so that he could play with his Xbox controller. He's got a grip where his trigger finger can move super quick because it only has to move a little bit. The motor's quite quick. So he can fire the gun when he's playing whatever game he wants to play really quick. You notice there that Kayden's hand is black. It's called Galaxy Black Filament because it's black with flecks of silver in it, and that is Kayden's choice of color there. And then he has, for the flexible filament, he has green, lime green, which he likes to use as well. So he's got a black and green hand. And the reason he picked that is because it wouldn't be completely different and completely obvious that it's a prosthetic arm, and that is what he has. So we now have, with all the electronics, with all the 3D printed parts, with the Xamarin app, we've got the price down to just over £500, so $680, what, 550, 60 pounds, euros, sorry, for all the components to make this hand. So instead of the many thousands for the NHS, we've got it down to around 500, which is awesome. I'm trialing some other motors I've got behind me, which I'm trialing out in another hands at the moment. You notice the Actronics motors is the biggest cost. 2/3 of the cost is the motors. These new motors are less than a third of that. So hopefully we can get the price down to around 300 to 350 pounds, similar euros, in the coming months for the next child we're hoping to help. So we will hopefully get the cost down even more, which means that we can do what we intended to do. One of the 3D printers I've got next to me has been built. We're hoping to take this to a hospital around the world when we're allowed to visit the hospitals again. And the idea is to drop the printer off with a box of plastic and all the springs, components, etc., and let them make them locally for the children locally, because they don't have the NHS that we have here in the UK, or a health service that you have wherever you are across Europe. They may not have that in the part of the world that they're in, so we're hoping to help them out. So what's next? We'll come on to that next. Let me hopefully be able to show you. If I drag onto my screen, this is my my phone that I've got here in front of me, and we are going to open up the Handy app. Going to collect the battery, and we will start scan. We'll notice Handy appears, and there's Handy. So this is the app. If we go into the UART, which is the serial protocol, we'll notice that it starts talking. And all we do is in the Bluetooth, we just have, you imagine when you print a console, so debug.writeline, all we do is we literally have, we've copied those kind of protocols across, and we have Bluetooth.writeline, and we write out to Bluetooth, and it comes across as a string. So this is all the commands that are carried across. You can see all the different commands you can send a string for G0, and it'll carry that command out. But if we go back to, these are big buttons. I can use, I'm using that called Visor here to screen share my my phone. But if you can see over my shoulder here is Handy. And if we do this, you can see Handy is closing into a grip, into a fist grip. And we can then go to a hook, which is to hold the shopping. Kayden asked for that to be removed because he never wants to help with the shopping, but his parents said it has to stay. And then we can say points. So it's going to point. It's over that way, my friend. So hopefully you can see that. If I bring it close to the camera, there we go. So you can see that it's moving, and that's there. So we can also go across to the grip order. You remember we said we've got those 5 grips. Maybe Kayden doesn't want them in this. He doesn't want fist, hook, point. He wants to have them in a completely different order. We can change the order, and we can switch the order around. Maybe he wants the order to be this, and my son is trying to call me. And we can save that back to hand, that we save back down. That'll be the new order that we uses. Maybe he wants to build his own grip. And this is the page we'll use there, where we'll slide to slide, we'll put it into builder mode, and we'll slide the sliders across and save the animation steps, and we'll do all that for us. And then we had the Bluetooth connection, which we went to before. Then we've got settings as well, where we can set the settings up, which now means that we no longer need to connect to a laptop. We no longer need to we no longer need to have special programming skills. We can do it all via a mobile app, which means that your hospital doctor or your parents or even the child can make their own grips. What's next though for the projects? Like I say, we can move across, and I'm in the process of doing this to build the Meadow F7 for WildernessLabs, which is all .NET and C# on the board as well. It gives us added advantage. The red box you can see off to the left there is an ESP32, which allows you to do over-the-air updates, which then means that when we want to update the board, we can push new software directly to the board via the mobile phone. Which then means we can update things remotely as well as doing it on the board as well. Why do I mention being a pilot? Like I say, we want to take this 3D printer, the one just to my left here, and we want to take it to a hospital. We've spoken to a couple of hospitals, one in India and one in Pakistan, and we're looking to take this printer to one of those 2 hospitals when we're allowed to go and visit them again. When we finish with COVID. Obviously, at the moment I can't fly because I'm suffering with COVID at the moment, which is why I'm not with you. But that's why I mentioned being a pilot. And just to end our slides, I just want to say thanks to Kayden and family. We've helped other families as well with this project, but without Kayden, we'd never have got where we are today. Without his family and their support, and his doctors and nurses that support him, we wouldn't have the product and the project we have now. If you want to reach out to me, my Twitter handle is at the side of the slides now. And if you want to jump in and help, if you find me on GitHub, you'll see all the Handy projects on there as well. And I'll open the floor to questions. I think I'm just about on time.
Yep, you're absolutely on time at the exact minute. Honestly, I doubt that we will have many questions, or maybe not even one question, because, well, you know the destiny of the last speaker of the day. Yeah, I mean, everybody's super tired, and also thinking about the party that Bill Stuff is having tonight. Get a minute, an online chat. Yeah.
How are you going to have the party without Dylan? Isn't he in COVID hell at home as well?
Dylan is, he is in quarantine or maybe even sick at the moment. I'm not really sure. But he, as a lead singer, will be singing online with his green screen studio and electric guitar. So yeah, the concert will happen. Gediminas was wondering online, it's not exactly a question for you, so I don't know if I should read it, but he was wondering, is anyone in Lithuania is working on a similar project? Which is a very decent question to ask. I don't know, maybe somebody in the event is working on such project.
I don't know. If anyone is, I'd love to hear from them. I'd like anywhere around the world, I'd love to hear from them because there's always ideas that I can share and they can share with me. We all learn from each other. It's open at the end of the day, so it'd be great if they reach out to me. It'd be fantastic. If anyone's looking for a hand because they need one for themselves or family member or a friend, then reach out to me and we can chat.
Yeah, and I think if somebody in this event is doing something similar, they would probably be in the audience right now. I mean, is anybody in the live audience? Yes, we have questions there. Let me come to you.
Hello, thank you for the nice presentation. I wanted to ask, how strong is the grip of this hand?
It's quite strong. We depower the motors a little so it doesn't crush anything because the motors can be quite powerful. Those to give you a handshake, it would be quite a strong grip. But the design has the fact that the fishing line that we use in this hand is a braided fishing line, and it's wrapped around the screw head. So if it grips too tight and tries to crush something, the fishing line will slip on the screw, which is why when you see it moving earlier, the two smaller fingers were slower because that slipped because you gripped something too tight a few weeks ago. So yeah, it is quite strong, but you can control how much of that power gets through to the motors. Again, it's one of the settings in the mobile app, so you can control that with what it does is when the motor is being told to move and the position isn't changing over a few milliseconds, you can tell it how long to wait for it to move, and I think it's around 20 milliseconds, something like this. If it doesn't see a change in movement over 20 milliseconds, it stops the motor. You can adjust that time. Obviously, if you leave it longer, it will keep trying to move and crush even more. These motors are quite powerful. They can apply quite a force. But yeah, it's a setting that we can play with. Great question, though.
Is it fast enough? I don't know, if you want to catch a ball.
Yes, it is. And if you go onto the OpenBionics website, they have some videos of some of the people they helped where they're literally catching a ball. So yeah, it is fast enough to be able to do that. And again, you can speed the motors up and down. The faster they move, the less accurate they are, because obviously they can, if they're going too fast, they'll overshoot their position a little. But yeah, you can catch a ball.
Okay, anyone else in the audience? Good, because I don't want to come back here after I walked all the way back. Just saying. And yeah, online I see we have no questions left. And well, though we have quite a lot of people watching still, so that's weird. Okay, so thank you, Clifford, a lot for blessing us for the second time at the same event. Are you talking tomorrow too?
I'm not, no, but hopefully I'll be there in person next year. I'm hoping, fingers crossed.
Well, we hope too, but it would be a great joke if you just showed a face to say hi tomorrow too. Okay, so thank you very much. Give a round of applause for Clifford before he logs off.
Thank you.